Thank you, Evgeny. Hello everyone. My name is Florian. I'm working as a research scientist with BMW. Yes, the car manufacturer, and it's my pleasure today to present to you my work about vector symbolic architectures. And basically, this is more or less a connection or a collection of the things that I did for my PhD. That I now successfully defended last year in December. And it's basically like a slightly changed presentation, similar to the one that I held for the defense. So I don't know about the format. I haven't been logged in for this webinar. So if there's anything unclear in the talk, or if I'm too fast or too slow, or if you want to ask questions in the middle, please feel free to do so. Yes, basically today I'm going to talk about vector symbolic architectures and my work, how I experimented with them for the use for automotive scene representation, and how that can be used in an automotive context. And I want to jump straight into the motivation. So when I talk about like automotive context or environment modeling, I mean in the context of autonomous driving, where we have a rich and redundant sensor set up, and the use of powerful machine learning components is increasing in recent years. But at the same time, these autonomous driving prototypes, they have limited onboard resources, but the machine learning and AI components require high processing power. But at the same time, these modern autonomous vehicle prototypes, they are still struggling with challenging driving situations, such as the one shown here. Whereas in contrast, human drivers are able to tackle such situations by using only their eyes as sensors. And according to the US National Highway Statistics Department, we're only making one fatal mistake in approximately 90 million miles driven. And we do so by using our brain, which consumes only roughly 20 watts of power, which is comparable to a lightning bulb. Whereas on the other hand, in autonomous driving, the majority of power is dedicated to computing. So there's definitely a gap and room for improvements. And in my thesis, I wanted to at least like approach some of these issues, and the focus is on a novel approach for automotive environment modeling, with the goal of generating high-level representations of the scenes, allowing for both symbolic manipulation and neural network learning. And the ingredients that I've been using are, of course, distributed representations, vector symbolic architectures, which also allow for implementation in spiky neural networks. So neural network learning is the second ingredient. And a little bit in parentheses, neuromorphic computing hardware, such as, for instance, Spinnaker or the Intel's Loihi chip, which would allow deployment and increased energy efficiency when those representations are implemented in spiky networks. So the research questions that I was focusing on is how could we encode automotive scenes in the substrate of distributed representations? And furthermore, do automotive tasks benefit from this kind of representation? So are these representations able to capture the semantics of the scene? And can neural learning algorithms leverage those representations for decision making? And finally, when looking at for instance, one of the tasks that I was focusing on, namely vehicle trajectory predictions, are the representations able to capture the mutual influence between traffic participants? And now I want to give you a quick outline. So we already looked at motivation and introduction. The next part will be about materials and methods. I will briefly go over the ingredients, the vector symbolic architectures, and how we use them to generate representations of automotive scenes. A short look at the capacity analysis, and then I will focus on automotive tasks, mainly on vehicle trajectory prediction, but also a brief look at how these representations could be used for anomaly detection, and I will conclude the talk by a quick summary and outlook. And I think for the next couple of slides, I can go very quickly over them because I think basically everyone in the audience is aware of that. So we're looking at vector symbolic architectures, and I am using a variant of the holographic reduced representations by Tony Plate, namely the semantic pointer architecture. And that means I have a subspace of a real valued vector space, element-wise addition and circular convolution, and the angle between the vectors, or the cosine similarity, is used as a measure of similarity. So vectors with a small angle between them are considered similar, and a large angle are considered dissimilar. And as I assume every one of you knows, that the nice property of these architectures is that two random vectors have a very high probability to be close to orthogonal, and which allows the retrieval of atomic vectors from structured representation, as shown in this very basic example below. And how can we now use this substrate to encode automotive scenes? And here I'm following the three-stage process suggested by Gallant and colleagues. So if we have an automotive scene such as this one, the first stage would be the pre-processing stage. So basically generating a vocabulary. So looking at what are the objects or items of interest to represent in the semantic vectors. For instance, in this example, this could be cars, traffic signs, traffic lights, and pedestrians, maybe bicyclists, motorcyclists, and then basically creating the vocabulary by assigning a vector representing this entity. Maybe also other concepts, intangible concepts such as green, to indicate the status of the traffic lights. And the second stage is the representation generation stage. So once we have generated a vocabulary, then I'm building up a representation of the scene. And this could, in this simple example, this could be simply by binding the vector representing pedestrian to some vector encoding its position, similar for the car, and binding the traffic lights to their status green, and a vector representing a traffic sign to its meaning, in this case yield. And finally, the output computation stage. Here I simply use the generated scene vector as input for a neural network to solve some sort of tasks. And in my thesis, I looked at driving context classification, very deeply in vehicle trajectory prediction, which is one of the main parts in this talk, and anomaly detection. Regarding vocabularies, I mainly focus on random vocabularies, but I also looked at manually engineered vocabularies and automatically learned vocabularies, but they didn't show much of an improvement or a difference at all. So this is why I'm neglecting them in this talk. So now I want to focus on how to encode numerical values, because if we want to encode like the position of traffic participants, we need a way to encode these numerical values of the positions in the vectors. So therefore, we need to look a little bit more into detail of circular convolution. So we can write circular convolution as a combination of the Fourier transform and its inverse. So to calculate circular convolution, we use the discrete Fourier transform of both vectors. And in the Fourier space, we employ element-wise multiplication and then use the inverse discrete Fourier transform to actually calculate the circular convolution. And with this definition, we can actually define a convolutive power by an exponent. So again, we use the same formula. We use the discrete Fourier transform applied to the vector v, then take the element-wise exponentiation by the exponent p, and transform that vector back to the original space using the inverse discrete Fourier transform. And since this can be a complex valued vector, I'm simply taking the real part of it. And to avoid the accumulation of noise in these representations, I use so-called unitary vectors as basis or as unit vectors, so to speak. And those are those vectors that preserve the length of the vectors when convolved with them. And so this puts us in the situation to finally encode 2D coordinates xi and yi by simply taking the convolutive power with random unitary vectors x and y, convolve them together, then we have the representation of one numerical vector, and to encode a series, we simply sum them up. And this is how this representation looks like. So this is one vector simply encoding one object of type T1 at position x1 and y1. And this is an example where we encode two objects of the same type at different locations. And we can already see that the similarity in those right-hand plots compared to one object decreases a little bit. So that's why I also looked at the capacity analysis here. So I need to find like bounds for how many objects can be encoded in this sort of representation before the similarity drops below a certain threshold where they cannot be distinguished anymore. So first of all, I looked at simple superposition, and therefore I generated a random vocabulary with member vectors mi and n non-member vectors ni, and calculate the scene vector, simply summing up the member vectors. And then the question is, how large can the number of those vectors become before the similarity between the scene vector and the members is not distinguishable anymore from the non-members. And this is a plot for 256 dimensional vectors, 512 dimensional vectors, and 1024 dimensional vectors. And as we can see, on the x-axis, we have the number of superpositions, and on the y-axis, the similarity. The blue box plots indicate the members, and the orange box plots indicate the non-members. And I looked at two similarity thresholds, and we can see that for 256 dimensional vectors, we're safe with up to 40 superpositions, and for 1024 dimensional vectors, we can even safely sum up 100 vectors. But and even if we use a weaker similarity threshold, these numbers go up accordingly. But we're not only interested in simple superposition, but also in the representations involving the convolutive power. So therefore, I conducted a slightly different experiment where I generated a vocabulary of vectors indicating the type, that's the TIs, and the unitary vectors indicating the units of the 2D coordinates. And then I calculated sets of natural numbers ki summing up to the total number of type vectors n, but ignoring permutations. And that's simply to generate a scene vector with the object type ti appearing ki times. So so basically, yeah, the object of type ti is appearing ki times. And we by summing up, we generate a scene vector encoding each position. And then again, I calculate the similarity between the scene vector and discrete position values. That's basically the same as I did for generating this visualization. And these similarities are denoted as similarity of a member if the position of the discrete position value is close to the actually encoded value. And then we get a similar plot. Here again, we have the similarity on the y-axis and the number of superpositions on the x-axis. And again, we can see that with a total number of roughly 10, we are still safe for 256 dimensional vectors, and for the higher dimensions, that's we are safe with at least 15 superpositions. But we are also interested in this number of superpositions per class, as we have seen in the example before. And here, again, now we have, again, the similarity on the y-axis, but now the number of superpositions per class on x-axis. And here we can see again that now the number of superpositions per class drops a little bit. So for the 256 dimensional vectors, we can safely add like up to 6 items per class. But we also have to note that the more items we add up, the noise of the non-members increases. So that's something to keep an eye on. But still, for the higher dimensional vectors, the similarity of the members is still high enough compared to the non-members to be distinguishable. And now I want to focus on and turn the attention to the task of vehicle trajectory prediction. And basically, the task here is now I want to start with an example here. So in the upper row, you can see the camera images from a BMW prototype vehicle, front view and rear view. And basically, the idea or the question is, how can we predict the motion of, or the positions of the target vehicle, which is indicated by a red box here, for the next couple of seconds. So in the lower row, this is a visualization of the positional data. So the ego vehicle is indicated by this black dot. The green dot indicates the position of the target vehicle, and the blue line indicates the past motion, and the orange line indicates the future motion, and these gray lines is the motion of the other vehicles. And basically, the idea is to predict the orange line based on the blue line and the solid gray lines. And before I want to talk about how I actually approached this this task, I want to show you the data that I've been using. So I'm using 2 data sets here, a BMW onboard data set, which is recorded with a BMW test vehicles onboard sensors, which is proprietary data. And the data comes in the form of pre-processed and already fused object lists with all information being recorded relative to the ego vehicle. And in contrast, I'm also using the NG Sim US Highway data set, which is recorded with external cameras observing a highway segment in California. This is publicly available data, but there is no ego vehicle involved. And regarding pre-processing, since we're using 2 data sets, I'm trying to predict 5 seconds into the future based on the previous 5 seconds. And to make the data sets as comparable as possible, I interpolated the data with equidistant time steps of length of a quarter second. Since both datasets come with different sampling frequencies, and for training and testing, I divided the vehicle samples into 90% training and 10% testing. So now let's look at one example scene and how we could encode this in a vector symbolic architecture type representation. So again, we have the camera images on the right-hand side, and a depiction or visualization of the positional data on the left-hand side. And the target vehicle that we're trying to predict here is again highlighted by a red box, and is in the positional data is encoded, indicated by the colored lines. And now we simply encode the positions of all the traffic participants as shown previously. So basically, we encode the positions using the convolutive power, convolve the position with the object type. So this could be car, motorcycle, truck, and we do this for all the objects. And for the target vehicle, we're simply convolving that one with an additional vector called target, indicating that this is the object or the vehicle that we're interested in. And this is how this representation looks like for the same scene. So here we see the representation or the similarity of the vector with the target vehicle, and here with all objects of type car. And we can see that we are able to successfully encode this positional data in the vectors. And since for the vehicle trajectory prediction task, we are interested in sequential data, so of the sequence of the past 5 seconds, we simply generate one vector for each moment in time. So every hyperplane in this plot is basically one vector used as input data for the learning models. And this is basically the learning models that we're using. So we're using the positional data and depending on the model, some auxiliary data, put that into a learning model and try to predict the position of the target vehicle. And the main architecture that I've been using is an LSTM network consisting of one encoder LSTM and one decoder LSTM. And additionally, I also use a very simple linear prediction model based on a constant velocity assumption. And to answer the question if the prediction accuracy of the model benefits from the information about other vehicles, because only so I'm looking at several learning models, but they only differ in their encoding of the input data, and only the input encoding using the convolutive power or have access to the motion of vehicles other than target. And this is to answer the question if the prediction accuracy of the models benefits from these information and from the encoding in this vector representation. And here you can see that these models only differ in the encoding of the input data. And as a reference model, I also use a simple feed-forward spiking model implemented using the neural engineering framework in the Nango simulator. And the answer to the question if the prediction accuracy benefits from that is kind of. So if we look at both at the complete data sets, the prediction accuracy is very similar. So here we have on the x-axis we have the time horizon into the future, on the y-axis the rooted mean square error in lateral and longitudinal direction. And as we can see, all the learning models perform very, very similarly. And therefore, I wanted to have a look at a more detailed analysis. Also, the spiking models, they are at least in the same ballpark. They are performing slightly worse, but therefore they offer a simpler alternative when energy efficiency, for example, is a key goal to look at. So, but since the models are performing so similarly, I looked at certain metrics to compare them. So here, what we see here is a comparison. So the blue bar indicates where the convolutive vector power performs best in y direction, and the orange bar indicates where one of the other model performs better. And we look at the distance between the target and the closest other vehicle, the distance between the target and the ego vehicle, and the total numbers of vehicles present in the scene. And the lower plot here simply is the difference between the blue and the orange bars in the upper plot. And hereby we can see that that in crowded situations where the distance between the target and the closest other vehicle is smaller than 20 meters, and where the distance between the target and the ego vehicle is smaller than 20 meters, whereas at the same time there are at least 3 other vehicles present in the scene, those are the type of situations where the models actually benefit from this kind of representation. So in summary, all models perform very similarly. Differences are only apparent in or visible in specific situations, and the spiking models offer a simpler alternative for potential deployment on neuromorphic hardware. So, but to investigate this a little bit more deeper, I wanted to focus on lane change samples as interesting samples. But here the problem is that the data sets are imbalanced. So what we can see here, the BMW data set consists of basically 86% sample straight driving, where we can only see a lane change in they are a lot less prominent. And for the ngSim dataset, this discrepancy is even higher, with 95% of the samples not containing a lane change performed by the target vehicle. So to investigate if this imbalance has an impact on the performance of the models, I conducted the following experiments. I trained all the models on the complete data set and only on the lane changes, and then evaluated those models on the complete validation set, only on the lane changes, on the crowded samples according to the metrics that I've introduced in the previous slides, and in the crowded samples that contain a lane change only. And here the results look a little bit different. So this is again the overall data set results, so trained on the complete data set and evaluated on the complete data set. And this is trained on the lane changes and evaluated only on the lane changes. And here we can see in Y direction where the main nonlinearity of the lane changes happens, that the models employing the vector representation outperform all the other models. And if we look at crowded lane changes, when we train on lane changes, then the discrepancy becomes even more apparent. And to see if the models, if there's a difference between, for instance, the numerical models, I also now plotted them against each other. So here now we can see the models, the numerical models with trained on all samples and trained only on the lane changes, and here the LSTM using the SPAR representation, also trained on all samples and the lane changes and evaluated on the lane changes. And here we can see that there's not much of a difference between the numerical LSTM given the training difference, but for the LSTMs using the vector representation, we can actually see a large difference. So if we train only on the lane changes, the performance becomes a lot better. And for the crowded lane changes, we have a similar approach. So thereby I conclude that this is not like a feature that you just simply train on the particular class of lane changes and then all the models improve. No, the numerical LSTM does not improve, but the vector representation does improve. So thereby I conclude that the additional information encoded about the other traffic participants is valuable and it's helpful, but you have to look very specifically in your data to actually unfold these differences. And I want to conclude this part of the talk with a little example. So this is a sequence again from the onboard data set. The vehicle that we're trying to predict is this one right behind the ego vehicle. And we can see that like when we have mainly straight driving, that already the linear prediction model already performs well, which we have seen in the previous analysis already. And that depending on the situation, that like it highly depends on the situation which model performs better than the other. And that is why I extended this vehicle trajectory prediction model with an online learning model. So basically, I used the predictions of the different learning models as input for a mixture of experts online learning model. But due to time reasons, I don't want to go into further detail here. So if you're interested, you can either contact me or look at this paper where we present this mixture of experts online learning model. Now I want to give you a little bit, I want to describe the anomaly detection tasks very briefly before I conclude with the summary. So basically the idea here is to use the same representation as for the vehicle trajectory prediction and see if we can find anomalies in the data. So I'm simply using the representation as input for a simple autoencoder network to generate reconstructions of the input vector, and then looking at the reconstruction error. If that reconstruction error exceeds a certain threshold, then we consider those vectors to be outliers. And since it's not possible to have a qualitative analysis here, I look again at the metrics that I've used in the previous analysis. So here we have again the distance between the target and the closest vehicle, and the distance to the ego vehicle, where the blue bars and boxes indicate the anomalies, and the orange bars and boxes indicate the complete data set. And we can see again that the anomalies detected by the network look very different. So again, these anomalies tend towards crowded situations with small distances, where we don't see this tendency too much in the overall data set. And similarly for the number of vehicles, again, the anomalies tend to be scenes with a large number of vehicles. This is the results for the BMW data set. For the NGSIM data set, the results or the differences are not that clear, but they are still visible. And that brings me to the summary of my talk. So the main contributions here are a novel approach to encode automotive scenes in the substrate of vector symbolic architectures, a novel representation for spatial positions of multiple objects. I investigated downstream applications such as driving context classification and very predominantly vehicle trajectory prediction. I analyzed the capacity of the vectors, influence of the data set, and also in my thesis there's an analysis on hyperparameters on performance. I also pointed you to the mixture of experts model that I also investigated but skipped in this talk. And future work could involve to replace the LSTM models with the novel Legendre memory units proposed by Volker and colleagues from University of Waterloo, to encode more and other information in the scene representation. And of course, something that I wanted to do but I couldn't do in the during my thesis, to deploy that representation and models on neuromorphic hardware. But in summary, those approaches investigated in my thesis show the promise to be an energy efficient addition to future automated vehicles when they will be able to deploy it on neuromorphic hardware. And yeah, that's basically it, what I wanted to tell you today. I think I'm a little bit over time. I apologize, but yeah, if you have any questions, feel free to either ask me now or feel free to get in touch via email. Thank you very much for your attention.
Thank you very much, Florian. Great talk. So now I open the floor for questions. So as I said, from now on until further notice, we will have one talk per webinar. So hopefully it will allow for more discussions. So please, anybody, unmute yourself and speak out. So.
Hi, Florian. Thanks, thanks for the talk. That was really interesting. So one question I have is, so you mentioned this as the sort of end goal being energy efficient analysis on these autonomous vehicles. So one thing that I was wondering about that is it seems like a lot of the complexity comes from analyzing the basic image that the scene that the car is receiving, right? So like estimating the depth to other things and like segmenting the image and stuff. So do you have a sense of what the trade-off is between the complexity of that kind of pre-processing the sensor data versus doing analysis on the process form the sensor data is?
Mm-hmm. Yes, so I moved over this part in the talk very briefly and quickly. So the input data that I'm using here is already pre-processed object lists. So I'm not concerned with like data pre-processing in terms of receiving an image or receiving LiDAR data or receiving radar data and then trying to make sense out of it and put that into the representation. Much rather, I already have like abstract object lists where I have like an object where with like properties of position and type and so on, which is already pre-processed. And you're right that this is like a very yeah, image processing and also processing of LiDAR data. That's something that consumes a lot of energy. But yeah, I can basically go back to my first slide. So here, this is an analysis of how much power is consumed by the different units or sensor units within the car. And as we can see, the computing is very predominant compared to, like, for instance, the amount of power that the camera itself is consuming. So yeah, I would definitely say there's room for improvement. And there's also lots of work that's going into like accelerating or making these components, doing the pre-processing more efficient, with neuromorphic computing being one branch of them, but also looking at traditional hardware. So yeah, I cannot give you any hard numbers regarding how much, for instance, image classification, how much energy that consumes. I would have to look that up. But does that kind of answer the question?
Yeah, it does. I mean, basically, it's just sort of this like question of, a lot of HD computing or these vector symbolic architectures for machine learning applications. A lot of the complexity is pushed into the encoding procedure, and so it's just interesting to think of like how the improvements in learning efficiency trade off with the complexity of encoding.
Yeah. So,
but yeah, no, that answers the question.
Yeah. So basically, the hope was, or the hypothesis when starting this out was that the representations would capture these like the influence between the traffic participants when we encode them, and with the analysis that I've conducted, I could kind of show that, where like when we train only on the lane changes, that then really the benefits become obvious. But you have to really dig deep to actually find those differences. And so yeah, I would hope for that, that to further proceed here. And maybe if someone is interested in this kind of thing, I would also be happy to like further work on this and maybe also collaborate. So if anyone is interested in this, please let me know.
Cool, thank you.
Yeah, thanks.
I have one question in the chat here from Nathan. You showed capacity statistics for multiple vectors length through 1024. What vector length did you use for the trajectory prediction? Are you muted?
Sorry. Yes. So for the vehicle trajectory prediction, I used 512 dimensional vectors. I also analyzed if higher dimensional vectors are benefiting, and I don't have that in this presentation, but increasing the vector dimensionality slightly improves the results, especially for the publicly available data set. But not that significantly. So the 512 dimensional vectors seem to be like a good trade-off between representational capacity and computing power restrictions, so to speak.
I have a question on of my own here. So you, for the analysis, you use the LSTM, which is kind of a deep architecture.
Yeah.
Did you try, or maybe if not, maybe you can have an idea how more lightweight architectures would behave here, like echo state networks, I mean, suitable for time series analysis.
Yeah. So let me just quickly go to back to that slide. So yeah, so I also looked at the simple feed-forward network, and the feed-forward network didn't use all the vectors, but only a sum of like the last vector, the middle vector, and the most recent vector, and that performed surprisingly well. So in the longitudinal direction, there's it's a little bit worse, but not that much worse. So that's the cyan and the pink line here, and so that's actually performing not too bad. So yeah, I haven't looked at other time series architectures, but that would be definitely interesting to look at, especially since the simple feed forward network perform quite well. So it would be definitely interesting to look at more lightweight architectures, and that's actually a very good point. Thanks.
Any more questions from the audience? So let's wait a couple of seconds.
Sure.
Maybe one last more kind of personal question. Are you continuing working on VSA's HD while at BMW, or are you doing something else now after?
Yeah, so this was basically the topic of my thesis. I would love to continue work in this fashion, but it's kind of still a niche thing, and to actually convince it's already hard to convince people at BMW, which is like a German car manufacturer, like solid engineering stuff like that. It's already hard to convince people to use traditional neural networks. So convincing people of using these high dimensional vectors and convincing them that it's actually useful, and implementing them even in spiking networks and neuromorphic computing, which most people don't really know what's the difference between traditional neural networks and this kind of networks. It's difficult, but I would love to continue work on this, and I'm planning to continue work here as much as my time at work allows it.
All right, thank you very much.
Of course.
Well, if there are no more questions in the audience, then I would like to thank Florian once again for the great talk. So the recording will be available online.